Hi, I'm Roman Stanek, founder and CEO of Good Data. Please join me as I talk about the future of BI and the key challenges of scaling real-time analytics. We will cover actionable insights, integration with AI and other advanced data techniques, personalizations, and most importantly, broader use of BI and analytics systems. These initiatives will define the successful organizations of tomorrow. I look forward to meeting you in person, and I wish you all a memorable CDOIQ Symposium.
Well, good morning, everyone, and welcome to our second session in Track 3 this morning. This is going to be another hour session. And our speaker today is Rashmi Gupta. She's with IBM. Going to talk about that question that's really been bothering all of us. What's going to happen when quantum computing, which it will, comes into play, and how will that affect our data world and security and many other things. So with that, I'm going to turn it over to Rashmi.
Thank you. Thank you so much. Welcome, everyone. Good afternoon to everyone in the room and to everyone else who is online. Thank you for joining it. First of all, I must say congratulations. Congratulations for being in the room, being in the session, because that proves that you have an innovative mindset and you are ready to embrace a new technological change, which is coming and catching up with in big waves. It's a data-driven revolution called quantum computing. So congratulations. But even before I start, I wanted to know how many of you are CDOs or operate in that capacity, or you're helping your CDO organization? Good number. And I cannot see it on the web, but I'm assuming, like, since this is a CDO conference, we have most of the folks who are directly or indirectly involved with the CDOs. How many of you know about quantum, or you're really interested in knowing about quantum? And basically, if you're in this room, you're definitely interested in knowing about quantum. So in today's session, we talk about quantum computing for chief data officers. And as we might say with any new technology, right, is it going to be really a leap of faith, or is it really be something which will be truly indigenously innovative, right? So with that said, I would like open up my presentation for everybody online. Please hold off your horses and send your questions, which we'll be tackling at the last 10 or 15 minutes towards the session. I promise I won't hold up you on for your lunch break, so let's get started. You can hear me properly, right? Okay, good, thank you. So today's agenda will be basically about, in a nutshell, as a primer for those C-level executives on knowing what quantum computing is about. There is also a follow-up session tomorrow where who are like true technologists and you want to do hands-on with some quantum computing. It's tomorrow. And there are 2 sessions tomorrow. This is basically at a very executive level what you need to know. The second topic which I want to cover is, now you know about quantum computing, how you can deploy it, and what are the use cases useful for you, and how we can help you. I'm not promoting IBM here, but still, we have a lot of resources, free and open, which you can really tap onto. Thirdly, as an organization or as a data organization, are you ready for the quantum? What steps you need to take to be quantum ready? We have some toolkits which you can use it for learning. We can also actually help as a part of our consulting. And then finally, what resources are out there for the quantum computing? As we dive into this presentation, I just want to tackle or talk about quantum computing in terms of 3 Ds. The very first one, quantum computing as a differentiator. The second one is, what is the data about quantum computing saying? Right? What is the market data? What are the other competitors doing? How does the space or the landscape look like? And the last one is about the deployability, right? So yes, I'm ready. I know about quantum. I understand it, and it is applicable in my business field, but for my business use cases. How do I deploy it? So those are the three different topics which I want to, and that will be the flow of the entire presentation. So as a CDO, right, being the leader of the organization, driving the data inside the organization, I think it becomes very important for a chief data officer to be having innovative mindset. And the reason why we said that is, if you see the top 3 reasons why any of the companies are market leaders in the spaces, either because they have a very unique proposition around their products or services, or they have a technology which is so unique and so unachievable that they are clearly market leaders in that space. And for having these two is the innovation which gets them there. They embrace it properly. They have a roadmap for embracing that innovation in a faster way so that they can acquire that market space or capitalize on it. So being a CDO, it becomes imperative for you to really understand what is that landscape of the new technology looks like. And being quantum of one of them, and that's why I said as soon as you entered into the room is congratulations, because the very first task of embracing a new change has come in here, and you are helping the business objectives of your company to be a market leader. So why quantum is a differentiator, and why do we think that quantum is going to change the world or bring the world peace? So let's take a little notch at a smaller notch, right? So if you see this picture, this clearly depicts like why quantum, like what is the differentiator behind the quantum. So the white space talks about all the problems which can be solved in today's world, right? This is like reading the emails, sending the video pictures, analyzing the pictures, streaming huge amount of video content. And then the light blue space all around are actual problems which are still out there which cannot be solved. And then quantum occupies that sweet spot where it extends what the computations which classical computers cannot solve are now solvable by quantum, like the factorization of huge prime numbers. Getting to the exponential search optimization problems, helping with the simulations of the molecular components. So that's why we think that quantum will be, in the near-term future, an extension of AI. That's what we feel. And it will help as we grow and mature in this organization. It will help start solving other bigger optimization and simulation problems. And as we go through this presentation in the last few slides, we will touch base upon these use cases where we have actually helped the companies. And it's an actual open consortium where you can go and look into these use cases. There are algorithms available where you can try on. So a lot of exciting stuff happening, a lot of collaboration happening in this space. The second point which we talked about was the second D around quantum, which is the data about the quantum. So what does quantum mean? Like what is actually quantum and how it is differentiated from the classical computing? In classical computing, the fundamental unit was 0 or 1. But now in qubit, or the quantum's fundamental unit is now qubit in that, or the quantum bit. Now the information, the fundamental unit of information, the qubit, is both 0 and 1 state, right? So now fundamentally we are different, right? And as we go to the next slides, I will talk about other principles of the quantum computing, right? And the operations are similar operations, what we used to have in classical computing using the gates. We used to have AND, NAND, OR gates. Here we have H gates, and there are several other algorithmic gates which are available. And the difference between the quantum circuits and the classical circuits is they change the state of the quantum object, right? So the quantum states are changed. So the any gate where you see the red is actually the state of the quantum where it has been changed. So that's the difference between the regular classical circuits and the quantum circuits. So in a nutshell, we are talking about entirely different technology here, which is a little bit differentiated from our classical computing and still evolving, right, as we talk through this. So As a leader in this space, as a primer, there are three basic quantum mechanics principles, right, which we apply in the quantum computing. The very first one being superposition, the second one being entanglement, and third being the interference. Anybody studied quantum mechanics or quantum physics here? Or you remember it? So superposition is basically a state or a combination, linear combination of the states of 0 and 1. So if you see graphically, it can be represented on the surface of the sphere. The upper or the 0 bit represents, 0 qubit represents the ground state. And the 1 or the south pole of the sphere represents the excited state. And when both 0 and 1 are in equilibrium, you're at the equator of the sphere, right? So think about the combinations or the states a qubit can happen or can be done in a linear combination, right? So you can imagine the plane or the surface of the sphere in which it can be represented. The second one is around entanglement. It's basically connecting two qubits together in such a way that one qubit is directly or immediately correlated with the another characteristics of other qubit, right? So if you look in the quantum circuit which we showed, the blue gates were representing the entanglement or the connection between the characteristics of those two qubits. The last but not least is the interference. Interference allows to use those two properties, the superposition and entanglement, in a way that the qubit's amplitude is modified. It can be modified constructively or destructively. So whenever we do these operations, our whole emphasis is to increase the amplitude or to reduce the noise in the calculations of the quantum. So now you're quantum experts, or at least know about the principles behind the quantum. The next one is about what and how we are using the quantum for. Where do we see using all these quantum mechanics principles in the real life to solve the business use cases? So the very first one, and I think this is the very near term, is modeling the physical processes of nature, right? So this we are using for drug discovery, nitrogen fixations, and finding the better batteries. The second one is around finding better patterns within the AI and ML processes. And this is where we talked about extension of the classical computing, right? And we have seen many of the companies are focusing their attention here. The third one is obtaining better optimization solutions. These optimizations can be in the financial services in terms of portfolio optimizations. Any financial services folks in the room? So you must have done the derivatives pricing. We'll touch upon JP Morgan Chase derivatives pricing use case very shortly. So that is one of the classic examples and how it exponentially speeds up those driving derivatives pricing. The next one around the optimization is around traffic scheduling on the flight scheduling operations, right? So that is another where we are seeing some adoption happening. The third one is around the simulations, the scenario simulations, right? And again, we are looking, and it's still a new field to explore, but we have seen a lot of use cases on the simulations also. This is an eye chart, I'm sorry for that, but these are all the use cases which we currently have, which I have listed out here. If you need any information, we can point you out to the research there, but there is a lot happening as a part of the consortium. We have also compiled a list by industry, so you can really pinpoint what will be the right use cases, or augment the use cases, right, with the classical computing. That would be other way to really gear up for the quantum computing. So now we know about the quantum computing. We elaborate on the data on the quantum computing, right? So what does the market data look like? Where are the people? What is the competition talking about? Where is the energy going in the quantum computing in the market? So as we talked about the near term, or in the horizon, when we say horizon 1 and 2, we see a lot of optimization happening both in the financial services industry and also in the healthcare for simulations. So, and there is also emphasis on the cybersecurity, where we see true random key generation using the quantum true numbers generation algorithms. So that's where we have seen most of that's the market data is telling us. I think the next chart is also very interesting, and I really like the way they have laid it out by industry and the growth. So if you see the quantum computing market size, currently, like at 2021, is little shy of $500 million, which is expected to grow to $5 trillion by 2023. That's a massive growth which we are expecting in next 7 to 8 years happening. And the major industries where we see that growth happening is life sciences, aerospace, and agriculture, right? And anybody here from aerospace industry? Because that's where we are seeing a lot of secure quantum communications happening, and so that there is no eavesdropping. And there are a lot of cool examples in the aerospace industry where we have the quantum communication use cases for secure communications. The other data which I wanted to share from the market was around the quantum computing landscape itself. So I usually get this question a lot, not from my grandma, but from my colleagues, right? So what is quantum computing? Is it a hardware? Is it a software? Is it a service? Is it a pure research? Or is it just a sample of some use cases? I would say it's all. It's the whole ecosystem which we are targeting, right? We have the quantum computers out there. They're evolving. They're going from 127 bits to a 4-digit figure very soon. They have various technologies. They have superconducting, ion trapping, and to name it, right? So we have various services companies really beefing up in this space on quantum computing, how they can slice up and dice up and get to the right use cases where we can augment and use the quantum computing. We have also seen a lot of research happening in this area, especially led by government and the academia-led. MIT is a great example. We have a partnership with MIT itself. We are extending partnership with other academias and other universities as we talk. We have created hubs over there where they can really help other partners to come and grow in their hubs as pure research work. We do see a lot of users coming in this space, right? Two of them, which I have already pointed out in our presentation a little bit later. But we see Department of Defense being one of them as one of the major users and promoting that cybersecurity out there. The other chart, I'm so sorry, it was an eye chart for me also here as I read this, but just to see the leaders in the space, right? And very interesting observation when we see the products and services. To the far left on the top, we see all the hyperscalers scrambling in that space. You have Google, you have Amazon, you have Microsoft. They're all coming with their own version of their services on the quantum computing. So a few minutes back, I was looking at Azure. They had the whole quantum services around you can get the quantum compute on the cloud. You can select what type of conductors you want, superconductors, IonQ, quantum computers you want. There are services, there are use cases, there are research, and I think similar to what we have been promoting at IBM too, right? And similar thing we have seen at Google and Amazon and rest of all other partners and the collaborators in this space. If you see the far right towards the topmost quadrant, the North Star, on the innovation side, I'm very proud to say that IBM leads that space in terms of the quantum computers they are rolling out, right? We just rolled out 127 qubit Eagle, and now we are gearing up for 1043 qubit, which will be an exponential scaling in terms of the quality of the circuits and the reliability of the circuits. Other ones in this space are Continuum and IonQ. So now we know about the data about the quantum. We know about some primer about the quantum. Why now? Why do you think this is the right time for you to embrace this technology? Do I wait, or should I take a little bit more steady approach, or I just jump into the bandwagon? I would say this is the right time. This is the tipping point. We have moved from the hardware scaling, right? We are continuously scaling the hardware from 127 qubits to 1,000 qubits actually happening next year. There are software developments which are happening for frictionless quantum computing, where basically the non-user of the quantum compute can actually go and start using it. They don't need to know a lot about quantum computing. Other things where we are doing is algorithmic improvements for greater circuit quality, capacity, and variety, right? So we are trying to improve significantly on the quantum circuit quality itself. There is an open innovation and collaboration happening every single day. And when I talk about every single day, we see 2 billion circuits being created per day on our IBM quantum services alone, right? So this is just a matrix from the IBM. There are several other providers out there in space, right? So yes, you're not too late. You can still start looking for the right use cases. But then that comes to our next point, right? The deployability, the third D about quantum. How to really deploy it, where do I start, right? Am I quantum ready? So the first thing which I would say is almost like doing data strategy kind of assessments, right? Like on the discovery of that. Where do I stand in the organization? What is the support, right? What is that C-level support coming from? Do I have the enough innovation fund, right? Is my organization ready to adapt to this? Do I have the right skills? Do I have the right training? What business problem I'm trying to solve, right? Is it something which was never solvable, or it was always being dealt with a lot of hurdles? Can I take that on as my business use case and scale it, prototype it, and commercialize it, right, as being the leader of data and really prove it upon the innovation? So I would say from the deployability perspective, I think you have to do a good strategic assessment and the discovery of your internal organization to be there, right? So that's one of the things which I would really advise to the folks here, right? Like really getting ready for it, embracing it, and really not jumping on directly onto the bandwagon. This is a demo out there for protein folding. This is basically an exercise to find the optimal protein structure with the lowest possible energy. This had been an intractable problem for classical computers so far, just because the range of possibilities there can be, right? With just 100 chain amino acid, it can be 10 to the power 47 conformations, which has to be run through the particular algorithm or the model, which was impossible for the classical computers. But using the quantum computing, we can really arrive at this protein molecular structure, which is of optimal energy. And the use cases which we see of the protein folding algorithms is definitely around new drug discovery, which can be really exponentially speeded up using the quantum computing. The other one which we see is around nitrogen fixations, right? The very serious agricultural problems, which can really be helped by using this molecular simulations. A great example of molecular simulation. And I promised I will have some real world use cases. So this is the one from JP Morgan Chase. This is around the European derivative pricing option calculations and coming up with the right pricing strategy. If you are in the financial services sector, this is the bread and butter, right? Pricing it right so that your profit can be maximized. But having that strategy, running those typical Monte Carlo simulations, I don't know how I saw there were 4 folks who worked on the quantum and some people here. How tedious it can be to run and rerun those Monte Carlo simulations, right? With the errors and the noise in those simulations. So here we have actually used Q amplitude estimation instead of Monte Carlo and got exponential speed up for this optimized circuit. We have these case studies available in case if you want, I can really definitely help you to point that out to you. The next example is around ExxonMobil. We have 500 LNG, liquefied natural gas ships, which are used to transport critical fuel supplies across the oceans. So what is so complex about it, right? You must be wondering. But just with 12 ships to really navigate it and optimize that, there are different decision points which have a lot of variability from the wind perspective, from the demand-supply perspective. Just the 12 ships can create 21 million different decision paths, right? Now you think about 500 different ships. Now you're talking about exponential increase in those parameters, right? Typical classical algorithms or ML and AI cannot scale up to that. So this is one of the other studies which we have done on the logistics side, right? So optimization on the logistics side. Talk about the supply chain issues which we are facing today, right? So which has a direct implication here as a use case. Last but not the least, on the deployability, the third D we talked about the deployability. These are some of the free and open and public resources which we can offer. The very first one is around the quantum research itself, the IBM Q experience. We have a lot of researchers and use cases out there. The second one is actually experiencing them on the cloud, right? The quantum computing on the cloud. You can have that Q experience and start using the real machines on the cloud, which is totally free and available publicly. There are different plans, options. There's a premium plan, there's a pay-as-you-go plan. The third one is around the software development kit. Again, open source Qiskit software kit, which you can download. And there are a lot of collaborations and the research around the IBM Q network, where there's a whole community which can help you with the already created and generated models, which you can get from the GitHub. So those are the few of the resources which can help you jumpstart this journey. I just want to reiterate, right, like the pace is there, right? People are racing towards this quantum supremacy or dominance. There are already 380, and this is just the figures or the numbers which I have from our IBM computing side. 380,000 registered users, 1.4 trillion hardware quantum circuits in total. Out of that, 3.25 billion are created typically in a day. 24 quantum computing systems are already there on the IBM cloud, and we are growing them significantly again. And 1,400 different scientific and research papers, right? And these are all published papers which are available for the consumption by the consortium. It's a growing network. It's growing fast. 181 total folks in the network today. Of that, 14 are our industry partners, 21 hubs. So these are the premium partners who can really help with the quantum computing for other smaller organizations. 53 members, 41 startups. So there has been a lot of startup momentum here in this space. 52 academic members and partners, and again, this number is growing, and this is where we have seen the most growth in terms of research last year. And again, we are really thankful to the MIT for helping us with this whole research project here. With that said, I would like to say thank you, and thank you for listening to this. We are always there, ready to help. If you have any questions, I'll take that on, but I would say that the mindset really helps. Now the next thing is to really take the steps to really use it in the real world use cases. Thank you.
Questions?
Thank you. Just a quick question about the infrastructure. I've followed this for some time, and I understand some nation states are investing heavily. And I'm also wondering about the state of the current infrastructure required to operate. Do you have the right chipsets and the right infrastructure?
Right. So as I said, right, it is now cloud computing based. So you can actually go and subscribe to those plans. There are 3 different plans which are available. I don't know if I have in this presentation or not, but I'll try to see. Yep, right there. So these are a few of the plans which are available from the terms of infrastructure itself, which you want to use, depending on the appetite and where you sit in the organization in the road mapping and planning. Some of the plans where we have seen the major growth is the premium plans, where the academia's research and the organizations, the premium partners themselves are investing a lot in. But I would say a day-to-day use where you want to really experiment, the best will be pay-as-you-go plan.
Do you see competition from governments?
Yes. But specifically, I will concentrate myself on US markets, domestic markets, instead of international markets right now. So I cannot comment on that one.
We have a question online. How is the pipeline of skills for quantum computing developing, and how can CDOs better prepare to interact with quantum-based solutions?
Sure. That's a great question, because I think skill set is scarce here, right? And we have a Qiskit development software kit, which we talked about it. There is another one called CERC, and there is a huge community. It's a very community-based programming where you can be part of that community, which can help you to really jumpstart with the already created models, APIs, callable stacks. So that's the way I would say to start with. There will be, it's a Python-like language. I won't say it is, there will be a learning curve there, but there are resources to help.
So thank you. This is fascinating. I've got to ask a couple of really stupid questions, so forgive me. On the one hand, these are entirely new computers that are not running on zeros and ones, right? Where there's no iOS, there's no Windows, there's no Linux. That this is entirely new. Some of the examples you gave were where there was application logic hardwired into circuits, right? But you're talking about SDKs and cloud plans and go use this thing. I'm having a trouble making the leap between entirely new computers that aren't running on zeros and ones to here's our SDK and go play with it. Am I the only one? Maybe?
No, I think that's a very valid question, right? So when we talk about the middleware or the Qiskit software kit, it is actually applying and using those principles through use of different algorithms, right? So, and different gates. So one of the popular gates is edge or hammered gate, which actually uses these principles, those 3 principles which I talked about, really utilizes that to compute and create those models in that middleware or the layer which is obscuring and really helping you for the frictionless quantum computing, right? For the users who are not quantum savvy right now. So that's the abstraction layer being provided. But internally, it is using those principles of quantum fundamentals, right? So another example is Grover search algorithm, right? Same thing, same principles. They are actually utilizing those superposition, entanglement, and interference principles natively, yeah.
Another question online, I think it's on everybody's mind, has to do with the future of data encryption.
Okay. Do you want me to answer this first, and then I can take the judgment? Okay. So encryption, cybersecurity, and quantum computing. You must have heard a lot, and that has been a buzzword. And the reason why that has been a buzzword is the encryption, which is done by classical computers, can be actually broken in 36 seconds, which can take 2,000 years for the regular classical computers by quantum computers. 36 seconds versus 2,000 years. So when I talk about a curse, this is basically what we are getting into. I remember yesterday we had Dr. Michael's presentation out there. We are good, we are getting gooder, but there are bad guys out there who are getting badder, right? So how can we beef up and use the whole quantum? They're based out of quantum true number generators, right? Random number generators, that's what they use for the encryption. And they are fail-safe encryptions where no eavesdropping can happen because they are dependent on the quantum state. So these keys use the quantum state. And if any alteration or any eavesdropping happens, the quantum state is altered. So the signal cannot be decrypted back at the sender level. So you know that there has been eavesdropping happen. And that's where it is being used in aerospace industry very well for secure quantum, extremely secure quantum communications. So when we talk about how do I beef up in this cybersecurity world where we see the whole encryption issue coming in with the quantum network really breaking them in 36 seconds, we beef up, we up our game, right? We understand those and we make them more secure, more encrypted, right? And we do it before those bad guys get to us.
Hi, Alex Vayner here with KPMG. So it's been about 20 years since I studied quantum computing in grad school, and I think there's been some advancements. So for me, the big disconnect to cognitive dissonance right now is that when it's implemented, right, quantum computing paradigm enables to do things like the prime factorization and the solution to all of the NP-complete problems instantaneously, which basically means that all of the traveling salesman problems, all the things we solve now with optimization, linear integer programming that find heuristic or probabilistic solutions to problems, they're obsolete. So what was confusing to me is it feels, from a theoretical perspective, binary. Either we have it and we've completely disrupted our entire world, forget about AI and machine learning, those things are not going to be that useful anymore, or we're not, and then what are we doing? So what am I missing? It seems like it's either we have it or we don't, but this seems like we're somewhere in between.
We are somewhere in between, right? Because if you remember when I showed you the classical bit versus quantum bit, classical bit is either 0 or 1, whereas quantum bit is 0 and 1 between the ground state and the excited state. So the way we are tackling it or making it as an extension of AI and ML is the input from the classical programming, right, is actually fed into the quantum state now. And now that's where the quantum computing, or it's called an extension of the AI and ML. And let's connect it a little bit later. We can refer it to the significant research on that topic and how to really do that. We already have some algorithms on that topic. How to feed from the classical computer information back into the quantum computers and utilize it from going forward there. By the way, I'm a KPMG alum too.
Had another question online. It's somewhat similar to what we saw in the last session about lift and shift. So is there ways to take the current classical bit models and transform them into quantum, into qubits, or is it take an entirely different way of approach?
So I think I just answered in the last question. Okay. It is an extension of that. We take the inputs from the classical computing and then feed it into the quantum states.
You don't have like a conversion algorithm to take?
I don't think we have evolved that far yet.
All right.
I too am very excited, but I'm going to raise your stupid question by one. Is when you went through this, you basically said we're going to have to ultimately rip and replace our data ecosystem, new hardware, new partners, new talent profile, and then the list of participants in quantum computing were, government entities, big universities. When do you think it becomes financially reasonable for companies of moderate size to invest in quantum computing?
So I will show you some data around that, right? Let the data speak about itself. It's an evolution, right? And with any evolution, take an example of blockchain. When did you feel that you have missed the boat? Or did you ever feel that you have missed the boat? Or did you see a real use case happening from the blockchain? And I think this is slightly different than the blockchain. This is more evolutionary, right? So it's your left, yes. So the diagram on the left is talking about the adoption, right? So where do we see that adoption happening in the real world, where we graduate from research, academia, and government to the real world companies and smaller companies? We have seen startups are really growing up in this space, right? But when it is really solving the real world problems, I would say in a range of 1 to 7 years. 2023 to 2030 is that horizon when we are evolving. And I think by 2030, we should see a significant adoption at that time.
Another question online. How does energy consumption of quantum and classical computing compare? Is it more resource intensive for quantum computing?
I can talk from the hardware perspective because at the application layer level, it will depend upon what kind of models you're using, how you're doing the computes. At the hardware level itself, I think the current challenge with the superconductors, the way they've been designed is like superconductor like aluminum or neodymium. They are sitting on a silicon substrate, and that has to be below freezing level, right? So at any point it goes above zero, the quantum state is lost, or we have a noise in there, right? Interference happens. So that challenge of being sub-zero, I would say is energy consumption at this point of time, and having to save those states, right, quantum states. That's the challenge which we see, which they are evolving. They're coming up with that frictionless quantum computing in next 2 to 3 years. Again, yes, I think it's a near-term horizon.
Well, just another question on my own, having to do with, I noticed in your slide, you were talking about the superposition, so it's only probable of having the right value. So we're not ready to replace banking systems with quantum computing for balancing accounts yet, right?
I cannot answer that because that algorithm was not designed by us, but these are the simulation or the optimization problems, right? We are not talking about replacing the entire banking system. We are talking about a piece where we can use the intelligence to speed up a process, right? So that's what we are talking about. We are one small piece in the entire ecosystem of the banking industry.
Because one of the issues is error rates when you try to do deterministic type of computing. Yeah, okay.
Thank you, Rashmi. This has been very interesting. In the life sciences space, specifically in drug discovery, obviously the simulations are a big component of that. And life sciences organizations have been very traditionally gun shy when it comes to using new technologies, especially as we move through from drug discovery in through the clinical trials. As we find out, we lose more and more money as we go through the value chain there. What kind of organizations are exploring this? Are these the 800-pound gorillas? Are these startups that are exploring this? Has there been any hesitation on the safety of these systems as these the identification of these molecules are their crown jewels?
I would answer slightly differently this question. We are working with 800-pound gorillas, and I cannot name them because of privacy issues. But there are smaller niche companies also coming up with their own kind of model for simulations, right? There's a lot of consortium and collaboration happening in that space within the smaller startups. And I showed up out there, right? There were good 20 to 25 startups, new startups happening. So we are seeing a whole ecosystem evolving in that. And again, drug discovery is a complex problem to solve. It takes years, right? What we are trying to do here is those scenario simulations which we are running, or the computation, exponential computations which were happening, now we can reduce that time. But still, there is the whole process around the clinical trials, right? Which you have to anyways deal with it, right? This is the technology where it is coming and helping you with speed of the actual molecular process, right? But you're aware, like the whole documentation and the process around the clinical trials, that will still be out there.
I think you've addressed all the questions that I see online. Any other questions here with the audience? Yes.
Thank you very much. So I actually played around with Qiskit a couple years ago, and what do you, for companies that are getting started in this, what sort of training or educational background, like linear algebra, et cetera, would you guys say is necessary for success?
We are creating the abstraction layer, and when I say we are talking from the Qiskit perspective. Similar thing is happening in the CERC also for non-quantum users, right? So that it becomes useful for them to really bring in this business acumen, and they can use the quantum for as a non-user, right? So that's what we're talking about, the frictionless computing, which is happening pretty soon, creating that abstraction layer, so they don't have to go through the whole college life again, which we dreaded.
Any other questions here in the audience? Thank you so much.
Thank you.